Good morning to you all. First of all, it's our pleasure to have had the chance to participate in this conference. I'm Sarah Boudouh. I'm a PhD student in University of Lagos Lab, Algeria. We will have a sneak peek to our work titled Breast Cancer, Breast Tumor Detection Using Deep Transfer Learning Techniques in Mammogram Images. Female breast cancer has now surpassed lung cancer as a leading cause of global cancer incidence in 2020, with an estimated 2.3 million new cases, representing 11.7% of all cancer cases. Among women, breast cancer accounts for 1 in 4 cancer cases and for 1 in 6 cancer deaths, ranking first for incidence in the vast majority of countries. Breast cancer can be detected using several imaging techniques. Mammogram imaging is the most often used technique to identify suspicious lumps in the breast. It allows radiologists to detect abnormal masses. Yet still, it is difficult to interpret the mammogram since lesions detection in it depends on radiologist's level of experience and also on image quality, which leads to diagnostic errors. The increase of abnormalities detection failures in the mammogram is due to the poor image quality, eye fatigue, or oversight of radiologists. Thus, it is needed now to assist doctors in diagnosing and detecting breast cancer, which will help to speed up the diagnostic process. In our presentation today, we'll see some state-of-the-art. We're gonna, after that, present our approach, and finally, we had a conclusion. In the topic of breast cancer detection and diagnosis, there has been a lot of research published. However, we'll focus today on those that did detection using mammogram images, which can be divided into 3 categories. Breast tumor detection, which is a binary classification of normal and abnormal mammogram images. Breast cancer detection, which is a multi-class classification of normal, benign, and malignant mammo images. And finally, a breast cancer detection, which is also binary classification but just for tumor cases, so the classes are benign and malignant, which is out of our topic today. In order to confirm the presence of a breast tumor, a binary classifier containing normal and abnormal mammography is required. To do so, the model must be able to distinguish between normal and abnormal breast tissue. Thereby, the region of interest in this case is the whole breast. On the other hand, in order to detect a tumor's type using a binary classifier with benign and malignant mammogram images, the ROI in this situation is the tumor area, so we don't need the whole mammography. Hence, to have a breast cancer detection model with great accuracy, we need to have a solid step 1 with a high accuracy, which is in this case tumor detection model. Then we can have a new one that is built based on the first one for tumor type detection. This was the main limit of several previous works where they addressed the problem with a multi-class classifier. So, we aim to propose an accurate breast tumor detection model as a first step into cancer detection. And, according to the preceding, our proposed study found that instead of using the commonly used small database Mini-MEOS with 322 images, we can take samples from 2 different databases in order to guarantee diversity in the images, balanced data, and a bigger amount of it, which leads to a well-trained model. In addition of that, we use transfer learning and data augmentation techniques to prevent imagery overfitting problems using a pre-trained convolutional neural networks AlexNet, VGG16, and VGG19 with then without trainable layers. In our approach, first of all, as mentioned before, we gathered data from 2 databases. The first one was a digital database for screening mammography, DDSM. We gathered 2,000 normal images as a sample from this one. And the second one, the Chinese mammography database, where 2,000 abnormal images mixed benign and malignant were added as a sample from this database. That made the total number of images in each class equal. The gathered mammogram images were pre-processed using several filters in order to extract the ROI, which is in this case the breast area, and remove the noise as well as the background. First, the binary filter was applied to the images, as you can see an example for each one. Then the resulting image was used to detect the largest blob, which is the breast area, and by multiplying the resulting image with the original one, all noise would be eliminated and we can get only the breast. But since the CMMD images doesn't have any noise except the background, the process was easier there. Next, we have the Wiener filter, which is considered as a noise removal filter. After that, the objective of construct enhancement is to improve the imagery low construct of mass pixels. Therefore, it is used in images that includes abnormalities. To accomplish that, we use the construct limited adaptive histogram equalization Clahy filter. After that, the data was split randomly to 75%, which is 3K images, as a training set, 5%, which is 200 images, as a validation set, and 20%, which is 800 images, as a testing set. To guarantee accurate evaluation, we reduced the amount of data in the validation set and added into testing one. Data augmentation is achieved through simple modifications such as a horizontal flip and zoom in and so on, so we used it on our training set. Then we have the transform learning, which is considered as a useful tool for problems where the dataset is not large. Finally, all the models were evaluated to determine how accurate they are, and the obtained results from each one were compared to each other in order to determine which one is the most suitable for our case. We were able to determine the accuracy, sensitivity, and specificity based on the results from the confusion matrix of each model. From the results, we can declare that using a pre-trained model without enabling the layers to train will not achieve great results, as opposite to allowing them to do so. However, in our case, it is clear from the results that VGG16 with trainable layers had 100% accuracy, which made it the most suitable model for breast tumor detection. Meanwhile, AlexNet's results were so close to the VGG16 with 99.5%. However, when compared to previous studies, especially the works which were in the same context of our work, our results were way better, as we can see. So to sum up, the results of this study shows an accurate breast tumor detection models, which proves that our approach was useful. The VGG16 had the best results among the others, with 100% accuracy, sensitivity, and specificity, which makes it the best pre-trained model for breast tumor detection with this dataset. We managed to prove also that using the pre-trained models without training the layers is not useful in our situation according to the results. Accordingly, the chosen filters in the pre-processing phase were well suited to our situation, putting our approach ahead of the existing ones. For future perspectives, adding another database to the collected dataset may have better results, since using two shipped great ones. Second, we can test the VGG16 with other pre-trained models such as ResNet 15, 101, Exception, LeanNet, and others. And finally, the most important thing, since the obtained models were accurate, especially VGG16, which could be useful as a solid first step for identifying the specific types of abnormalities, such as benign and malignant, it dives even further into the subtype of a single kind, such as masses and calcifications. Therefore, we can assert that what we accomplished could be used as a starting point for future research. This could help achieve better results in breast tumor type detection, and that leads to an accurate computer-aided diagnosis systems for breast cancer. Thank you for your attention, and happy to answer any of your questions.